Okay, so the first problem is gravel is being dumped from a conveyor belt at a rate of 200 feet cubed per minute, forming a conical pile whose base is diameter is 2 times the altitude. How fast is the height changing when the pile is 12 foot high? So the first thing I tell you guys to do is write down everything that you know and draw any pictures. So I'm going to go ahead and draw a picture. And we have this sand or gravel, and it's being dumped 100 cubic feet per minute. And actually, I want to just say something right here. Let's go with this. 100 cubic feet per minute. So right away, I'm thinking this here is telling me that we're dealing with volume. How do I know that? Well, because if you have any units to the third power, that means volume. And you should always be thinking, if you have units to the second power, you should be thinking area. And if you just have units, you should be thinking either perimeter or circumference. So units to the third power, that means here it says feet cubed. So that's written like that. You could see it written as cubic feet, or in centimeters, you'll see them write something like cubic centimeters. And once you see that, you know you're dealing with volume. Now let's get back to what's going on and what we know. First thing I want to see is gravel's being dumped at a rate of 100 feet cubed per minute. So it's making a conical pile whose base is 2 times the altitude. So I know this is making some kind of a cone. So when you pour something, if you just kind of picture something being poured, all this sand being poured, and as it lands in a cone. And the base is 2 times the altitude. So that's going to be important. The base of the diameter is 2 times the altitude. How fast is the height changing? How fast is the height changing? They want to know the change in height. So you're thinking dH dt. All right, so let's go ahead and I'm going to make this a little nicer and label some things. So we know as gravel is dropping, right? We know that it's getting higher and higher. So your volume is getting more and more. So that's something you want to remember. It means that we have a positive rate of plus 100 centimeters, 100 feet cubed. And we know that the diameter, so let's talk about what we know. We know that the diameter is equal to, I don't like this color. I was just using it for sand color. I'm going to change it. Okay, so we know that the diameter is equal to whatever this height that's changing here, as it's getting higher and higher and higher. We know that the diameter is double that height. So we know that the radius is equal to whatever double the height is divided by 2, because that's radius when you divide by 2. So that means radius is equal to height in this one. So this is a pretty straightforward problem, considering the other kinds that we're going to have. So in this case, I'm going to go ahead and just put, I'm talking about volume. I know I'm talking about a cone, so I know I'm talking about volume of a cone. Volume is equal to 1/3 pi r squared times h. But now we just proved that r is equal to h, or we just showed it. So in this problem, so volume is going to equal pi/3 h squared times h. But that means that it's just equal to 1/3 pi times h cubed. That's what the volume is. Now they want to know how fast the height is changing. So they want dh dt. Okay, so we're going to want dh dt. And that's why we did this with radius. We didn't want to have these two unknowns. So we were like, okay, well, they kind of set this one up. They spoon fed it to you, but it's something where you want to try and get just one unknown, like volume to equal one unknown. And since we're looking for dh dt, we wanted to leave that into this equation. So we wanted so we wanted h. So now we're going to go ahead and take the derivative of both sides. And that's going to give me let's see if I can. No, I can't. I don't want to erase all this. So hopefully you guys can pause since there's nobody here today. That's going to give me, I'm going to start from the get-go from here. Okay, so I'm going to take this, I'm going to erase everything and write that down. And on my PowerPoint, I have to erase it a little bit. For some reason, I can't just take a whole section like I usually can. So we're going to go ahead and take the derivative of this. V is equal to 1/3 pi h to the third power. And that's going to give me dv dt is equal to 1/3 pi times 3, right? Because I got to take the derivative here. So it's going to be times 3h squared, but we're taking the derivative with respect to time, so it's dh dt. And let's go ahead and clean it up. dv dt, there should be a capital V, is equal to, now this is really 9h squared to the third power. And hold on one second. What am I doing? That's not 9. I don't know why I just did that. That's just what it is. I was squaring it like as the square was on the outside of the parentheses. Let me just check. All right, we're good. Yes. All right, so back to where I was. So I'm going to clean it up again. So these cancel. And then I got to plug in some things. So I'm going to have, instead of dv dt here, I know what dv dt is. It's up in the formula or in the original sentence here. It's 100 cubed per minute. That's the change in volume per minute. dV is change in volume, dt is per minute. So that's 100 centimeters cubed per minute is equal to, now I'm left with pi. The height is 12 feet high is when they want to know the change. So I'm going to plug that in, and that's squared dH dt, and that's our unknown, dH dt. Now I just divide both sides. I'm trying to get this dH dt alone right here. So I'm going to divide both sides. This is 144 pi, so I divide both sides by 144 pi. That equals dH dt. And that reduces, and you can work it out in your calculator. I'm not going to do it this time, but that reduces to 25 over 36 pi. And that's equal to, let me do this. I want to tell you something so you understand it. That's equal to dH, which is the feet, the height, the change in height is going to be in feet. So you know it's feet. Then this is the per, but I'm going to put it here. And dt, well, we're in minutes here, so that's per minute. Feet per minute. That's what we want our answer in, and that's what it's in. All right, so let's move on to the next slide. Sand is being poured into a conical shape at a rate of 4 inches squared per second. If the radius is half the height of the cone, what is the rate that the height is changing when the pile is 16 inches high? I just want to talk about something really quickly. If you're pouring sand, let's say at the beach, and you pick up and you're a bucket and you just pour sand so that it trickles and it eventually makes some kind of a cone. Okay, because as it goes, it starts to trickle all around here. And then the sand gets skinnier and skinnier as it gets to the top. There's always a relationship between the radius and the height. It's always some kind of relationship between the radius and the height. In this case, they're telling us the relationship, but there is always some kind of relationship. As the height gets bigger, maybe the radius is getting smaller. This could be upside down. So there's always some kind of relationship. It's either 1/3 as much, 1/4 as much, something like that. But there is always a relationship in a cone between a changing height and a changing radius. So keeping that in mind, let's just go through this one now. So remember that that rate of change with the radius is constant with the rate of change of the height. And that's just it's just like something important that you want to keep in mind. I think this is wrong. That should be cubed, cubic, cubed, 4 inches cubed per second. So, all right, so let's talk about what we know. I know that it's a cone. I know that dV dt, it's telling me right here, is equal to 4 inches cubed per second. I also know that the radius is equal to 1/2 the height. And I know, well, it's not what I know, it's my unknown. Oh, I know at height equals 16 inches. We know we're going to be looking for it then. What is dH/dt? That's what we want to know. What is the change in height? Because that's what it says here. What is the rate that the height is changing? So I'll go ahead and use, I also know the formula I need to use. It's volume. You know, when you're thinking of these related rate problems, you know it's a related rate problem from that. And you're thinking, oh, is this going to be something where I'm going to use Pythagorean theorem? Or do I have to think of a geometry formula? Is this got something to do with velocity? Is this one of those rate of changes? You always got to kind of get your mind into what you're dealing with. And right now we're dealing with these. So that's going to be 1/3 pi r squared times h. That's our formula we're using. But we're looking for dH/dt, and there's these two. We don't want, like this we already know, okay, is part of our volume formula. But the problem here is these two unknowns. The problems are these two unknowns. Okay, you only want one on this side. So we're going to use this in terms of h, because that's what we're looking for. That's our unknown right here. So I'm going to plug that in. I'm going to substitute it in. And let's go ahead and just substitute it because they gave us the radius here. So I'll have now volume is equal to 1/3 pi times half h, because that's the radius, squared times height. So my change in volume, which is one of our knowns, so I'm getting happy here because I'm like, okay, I see some stuff happening. That's going to equal, and let's just call this 1/4 h squared times h. Let's make that even prettier. dV dt, it's not dV dt yet. I shouldn't even be writing this, dV dt. Let's just keep it with v. We haven't taken any derivative yet, so I was just thinking ahead of myself. So now volume is equal to 1/12 pi h cubed. Now I can take dV dt. So now I want to do this. And that'll give me dV dt is equal to, or let's not even, now we're going to, well, we know dV dt. So I'm just going to go ahead and put it in. I know it because it's one of my knowns. So I'm going to go ahead and put it in. So it'll be 4 is equal to, and I'll do this on the side here. You're going to take 3 times its 12th, and that's just going to give you 1/4 pi. And then we have our height. Well, it told us our height right here. So that's going to be times 16. And now that's squared because of the n minus 1 for the power rule. So that's squared. And that means now we can have, let's just clean it up. I'm going to erase this. We don't need these unknowns. I mean, these knowns and unknowns. Hopefully you're writing these down. Hopefully every time you watch a video, you write everything down and you try and work the problems out. So that's going to give me 4 is equal to 64 pi after you do all this work. I think that's 256. Then you divide it by 4, and that's going to give me 64 pi. Oh, and I forgot, we were taking it with respect to time, so you had to write dH/dt. So you have to have dH/dt here. And that gives me 1/16 pi is equal to dH/dt. And you can probably leave your number like your answer like this, but they might ask for a decimal. And let me just look real fast. I think it's 0.0. It's like 0.019 something something. So I'll just say 0.0199. And dH, what's our height? Inches. So it's inches per, what's our time that we've got here? What are we doing? What's our time units? Seconds. So this is inches per second, and that should say inches per second also if you leave it that way. All right, let's go into the next example. A 10-centimeter tall funnel is being drained with water at a constant rate of, I think that's supposed to say something different. I'm going to have to check it. Mouth is 12 centimeters in diameter. How fast is the solution level dropping when there is 200 cubic centimeters left in the tunnel? Yeah, that was supposed to be 10, and I just changed it, centimeters. So it's 10 centimeters per second. All right, so let's talk about what we know. It's height, we know it. It's being drained. We're dealing with a minus here. Constant rate, this is probably a related rates problem. And 10 centimeters is being drained of water, 10 cubic centimeters. So that's telling me volume. CC, cubic centimeters, anything cubed, remember, is volume. So I'm thinking volume in here. This is what should be going on in my mind. All right, so the mouth is 12 centimeters in diameter. All right, that's something else I know. That's one of my knowns. How fast is the solution level dropping? So we need to know the level, how much it's dropping when there's 200 cc's left. So I know that I'm dealing with a dV/dt. We already know this is a cone. This is our third one, cone problem. So I'm going to go ahead and write some things down in my head. Well, not in my head, but up here. Volume is equal to 1/3 pi r squared. I'm writing things down that are going on in my head. I know its constant height is going to be 10 centimeters. And I know that the radius, because the diameter is 12, so I know my radius, because that's what I want to put in here, is 6 centimeters. How fast is the solution dropping? So that's how fast is the height, the level, okay, when they're saying that. So they want to know the change in height. Since it's dropping, we know negative. They want that level. They want to know what the level is, how it's dropping. Now here's the problem. This time, actually, let's put our volume. We know when the volume equals, I should have these out of order, but in a different order. This should come before dH/dt, but all right, so I also know that dV/dt is negative 10 centimeters cubed per cubic centimeters per, what's my time? Seconds. But this negative, I want to make sure you put that down. All right, so let's go ahead and draw what we have. I know that this is going to look like this because it's a funnel. Okay, I know my radius is 6. That's a known. Now this height is 10. Okay, but I'm going to have a new radius here, and they didn't give me any kind of a relationship this time. They didn't say the radius is half the height. They didn't say the radius is a third the height. So I got to figure this one out on my own. So what I'm thinking is, all right, well, this is my water, and that's the new radius. And when it's a new radius, there's this new height. So I have to use what I know. And on this case, I don't, I think I have similar triangles. And remember, I've said that. It's usually Pythagorean theorem, a geometry formula, or your similar triangles. And I said that in the last video. So I'm going to go ahead and use the similar triangles. Now this 10, I want it to be clear. This 10 is for the big triangle here, this whole length from here to here. And then I have this new radius and I have this new height. And I'm going to go ahead and set up a proportion. So I have these two, you got the big radius, you got and big triangle, and then you got the smaller triangle. This is 6, this is R, this is 10, this is H. And this R is horrible. All right, so let's go ahead and set up a proportion. I'm going to use 6 is to R as 10 is to H. Some people might go 6 is to 10 as R is to H. Just make sure you're consistent. If you go this part of this triangle is to this part of this triangle, then you're consistent here. But if I'm going top is to top as height is to height, so I'm going to go 6 is to R as 10 is to H. And that leaves me with 10R is equal to H. Now, what am I going to solve? I'm sorry, is going to equal to 6H. What am I going to solve for? Am I going to solve for the R or the H? Well, I'm looking for dH dt. So that's the one that I want to be the variable in everything I'm doing. So I'm going to solve for H. I'm going to get H alone. I'm not going to solve for, I'm going to solve so that H is in there. You don't want it to be R. So you're going to solve for whatever R is so you can substitute the H. So I'm going to get R alone. So that's going to be 6 over 10H. See, because then I can put the H in there. If I would have solved for H, then it would have been another R in there. So the idea is to try and get it in terms of H. And that's just going to reduce to 3/5 H. Now I'm going to take this. I know this. I'm going to put this here. R is equal to, the new R is equal to 3/5 R, or H, okay? So now that we've got the similar triangles set up, let me erase all this. And I'm going to have a new formula. So I have the volume is equal to 1/3 pi times radius squared. So we just said the radius that we're dealing with is the 3/5 H. So that's going to be 9/25 H squared. That was for this part, times H. So volume is equal to, after I do all this work, it's going to equal, okay, let's do this. 3 goes into 9. Okay, so I did some of them just really quick, and I'm going to have 3/25 H, oops, let's say pi H to the third. Now I want to take and get H alone. So I'm going to have, let's go ahead and multiply both sides by 25/3 pi and 25/3 pi. And that's going to give me 25/3 pi times the volume, which was 200. So I have to have this, let's make this, I'll just rewrite it. 25/3 pi times your volume, which is right here. What is the volume? That was hard. I got stuck for a second. It's like, oh yeah, there's the volume. Okay. This volume looks like an R. I got to change that. So 25/3 pi times 200 is equal to H cubed. So this gives me 5,000/3 pi is equal to H cubed. So to get rid of that, I got to cube root both sides, or take the cube root. So I'm going to do that. And my answer ends up being about 8.1 for the height. So now I got to plug that in back into the formula. And that's going to give me -10, because I want dV dt, is equal to 9 pi. Well, we did all that to get these two things, right? So I've got 9 pi over 25 times 8.1 squared. I'm running out of room. Times dH dt, because that's what we're looking for. We're still trying to find this. So we need a dV dt to use it, because we wanted to take the derivative of our volume formula. And after you do all your work here, I'm going to do it. After you do all this work here, so let's say we got -10, because that was dV dt, is equal to 9 pi over 25 times 8.1 squared, because that's what we found, dH dt. And that's because we were trying to find the change. So we had to use the change in volume. We had to take the derivative of the whole volume formula. And that's going to end up giving you, after you do all this work and you get dH alone, dH dt is going to equal -0.13 centimeters per second. Height is in centimeters. Your time here is in seconds. So it's centimeters per second. All right, water is being poured into a cone shape at a rate of 50 cubic centimeters per second. If the cup has a height of 8 centimeters and a maximum radius of 3 centimeters, how fast is the water rising when it's 4 centimeters full? Okay, so rate, we got a related rates problem. 50 cubic centimeters, that means volume. The height, with something we know, is 8 centimeters, and the maximum radius is 3 centimeters. How fast is the water rising? That means change in height. So that's dH/dt. When it's this full, I think it should say that full, but we'll see. All right. Okay, so I told you everything you know. We should be doing this a little more quickly now. You should be kind of already starting. And we know centimeters cubed, and that should have said centimeters. We know centimeters cubed. Okay, it's going to be dV dt. So I'm going to draw this. And I know that the maximum radius I'm going to get is 30 centimeters. I'm sorry, 3. That's what it says, right? 3? All right, and it's 8 centimeters tall. I better not write that up. Let's write it on the outside. So we know it's 8 centimeters tall. And I also know at some point it's going to be right here. And we want to know, what is this radius going to be? That's the radius that we really aren't going to know. And that's at the height 4. And they didn't give us anything about a relationship with the height and the radius. So that means more work. What's some other things I want to write down? dV dt. That's 50 centimeters cubed per second. How fast is it rising? That means it's dH dt that we're looking for. What formula? Oh, but of course, 1/3 pi r squared h. We have 2 variables here. We want to get it in terms of h. It didn't ask. It's dH dt, so we want it in terms of h. So that means we kind of want to write it without the r. So we want to plug in the r. We want to replace the r instead. So the radius and the height are related. So I'm going to use similar triangles because they didn't give it to us. So you got to use the similar triangle trick. So you have these 2 triangles. So that's this triangle here and this big triangle here. Okay. Oops, I shouldn't have done that. That's this triangle. That's this triangle and this big triangle. And I know this is 3. This is r, and I know you see Like you want to use this, you know, you want to use things that you think, but you want to keep these R and H things like they, you want to use this 4 as height, but that's not what we're doing. Keep it in a variable because they want to know what the change is, how it's changing at that height. All right. If you were to put 4 and then take dH dt, you're going to be with 0. So you have to have height, right? Because the derivative is going to be 0 there. So you don't want to do that to yourself. So you put 3, and then we know this is 8. So I'm going to go ahead and use 3 is to 8, or 8 is to 3. You pick. 8 is to 3 as H is to R. So that means I'm going to have 8R equals 3H. I'm trying to write this with no R, so I need to find out what the R is to replace it. So find out what the R is to replace it with an H1. So then I'm going to go ahead and rewrite, and I'll have, the whole idea here is we're trying to write dV dt is equal to the formula of dV dt and the change dH dt, okay? Let me make some room. I'm trying to hurry this up so that we get through it. So then I'm going to go ahead and write it. The volume is equal to 1/3 pi r squared h. So the volume is equal to 1/3 pi times 3/8 h squared times h. And that's going to equal 9 pi, that's a funny looking pi. H to the third, because you're going to square this, all over, this is going to be 64 times 3, but I'm going to leave it like this so that I can cancel here and work it out. See? And then times h to the third. We already did that. Okay, so see how I can just do 3 goes into 9, 3. So that leaves me with 3 pi h to the third over 64 for volume. But now I want to take, I hate to erase everything, but all right, so now I'm going to take volume is equal to 3 pi h to the third over 64, but I want to find out the change in height. So I want dH. So let's take the derivative of both sides, and I'm going to end up with dV dt is equal to all right, so I've got that. Pretty much I just rewrote what I had on top, but now I wish I didn't erase it, but we did have in our list of knowns that dV dt, and I can always come up here and look, is 50 cubic centimeters, right, per second. So I have 50 is equal to 3 pi over 64 times this 3 times 4 squared dH dt. And the 4 comes because when you take the derivative, let me rewrite this part. You're going to have 3 pi over 64. When you take this, it's going to be times 3h squared, right? dh dt. And h, the 4, is when it's there. So that's what I'm plugging in. And I don't know dh dt. So that's where I got the 4. I took the derivative, got this, and then plugged in h. So now that gives me, after working everything out, I'm going to end up with 200 is equal to dh dt. And what are my units? Well, I'm in centimeters, because it's centimeters, per, and what's my time? I want to, per second. And that's your answer. So just understand that your cone problem, you got to understand some things. You see the question, it's talking about a rate of, you're dealing with a related rates problem. It's a cone, probably going to be using the formula for a cone. If they give you some kind of relationship, which will always be constant, between the radius and the height of the cone, you're good. But if not, you got to use similar triangles, get it in terms of where it's written with h in it, or they might ask about the radius and you'll go the other way. But you want to make sure that you only have one variable that you're plugging in before you take the derivative of everything. If you have any questions, please contact your teacher. Great.